Welcome to our fourth and final video for Chapter 13, Testing the Effectiveness of Antiseptics and Disinfectants. In this final section, we'll look at how scientists and manufacturers evaluate disinfectants and antiseptics to ensure they're working as intended. Before we dive into testing, let's first review the levels of germicidal activity. So high-level germicides kill all microbes, including endospores, and examples include glutaraldehyde and formaldehyde. Intermediate-level germicides kill most microbes, but not endospores, and these include chemicals like alcohols, iodine, and chlorine compounds. Our low-level germicides target only vegetative cells and some enveloped viruses, like soaps and detergents. So the effectiveness of these germicides really depends on their concentration, the time of exposure, temperature, and pH. And all of these factors can change how potent a chemical is in practice. This checkpoint asks, what are the differences between the three levels of disinfectant effectiveness? So we just saw this. High-level disinfectants are sterilants. They kill all microbes, including vegetative cells, fungi, viruses, and endospores with enough or prolonged exposure. So these can achieve sterilization. These include glutaraldehyde or even hydrogen peroxide at very high concentration. For intermediate level disinfectants, these kill vegetative cells, fungi, and most viruses, but not endospores. So examples of intermediate level disinfectants are alcohols or phenolics, some halogens. For low level disinfectants, these only kill vegetative cells and some can destroy some enveloped viruses, but they're not effective against endospores and not effective against non-enveloped viruses. So we said soaps are in this category. Some quats are also in this category. All right, let's jump into testing. The phenol coefficient test was one of the earliest ways used to measure disinfectant effectiveness, and it compares a chemical's ability to kill microbes with that of the chemical phenol. And in the past, we used two test organisms, Staphylococcus aureus, which is a gram-positive bacterium, and Salmonella enterica serovar typhi, or S. typhi. This is a gram-negative bacterium. It's a specific strain of Salmonella bacteria that affects humans. So a phenol coefficient greater than 1 means that the chemical you're testing, that disinfectant you're testing, is more effective than phenol. If you get a coefficient less than 1, that means it's less effective than phenol. So here are some examples down here. Formalin had a coefficient, or has a coefficient of 0.3. So this is against S. aureus. That tells us it's less effective than phenol. Whereas the chemical chloramine has a coefficient of 133, showing that it's far stronger than phenol at killing S. aureus. And although the test is rarely used today due to arbitrary conditions, it's historically important for standardizing disinfectant testing. The next test is the disc diffusion test, and we'll be doing this in lab as well. So this is a simple and visual test that we use to compare the relative effectiveness of different chemical agents. So how it works is we're going to take an agar plate and cover it with bacteria. So it's covered with a bacterial lawn. Then we take these small paper discs, kind of like this filter paper, and each disc was soaked in a different disinfectant or antimicrobial drug. We're going to take these discs and place them on the surface of the bacterial lawn. And as these antimicrobial drugs or chemicals diffuse outward, they're going to inhibit bacterial growth. And that generates these clear zones with no growth we call zones of inhibition. In general, the larger the zone of inhibition, the more effective the disinfectant or chemical. But only if the diffusion rates of the different chemicals are similar as they diffuse across the agar. So this test provides a pretty quick visual comparison, although it's not quantitative, and it can't account for differences in diffusion of the chemical or solubility of the chemical across the agar plate. So here's what that disc diffusion method looks like. We have an agar plate and we cover it with bacteria, so all of this cream-colored material is growth, the bacterium. Then we place these discs that are soaked in different chemicals. In this case, let's pretend they're different antibiotics. We're testing 5 different antibiotics. If these 5 drugs all diffuse across the agar at the same rate, then we can assume that the largest zone of inhibition, where there's no growth, is the most effective drug. So antibiotic number 5 looks like it's working the best here. And we can determine this by measuring the diameter of the zone of inhibition. But sometimes the drugs or the chemicals you're testing don't diffuse across the agar at the same rate. And in that case, you'll have to look at a standardized chart to see whether or not this drug is effective against this microbe. Here I can see this microbe looks like it's resistant to the 3 antimicrobial agents here, but it's sensitive to this one. It's being killed by that one. Here I can see on the plate on the right, this bacterium is very sensitive to these 3 antimicrobial drugs, but not as sensitive to that one on the upper right. This checkpoint asks, when comparing the activities of 2 disinfectants against the same microbe using that disc diffusion assay and assuming both disinfectants are water soluble and both can easily diffuse in the agar, would a more effective disinfectant have a larger zone of inhibition or a smaller one? So the more effective disinfectant would produce a larger zone of inhibition. That clear zone around the discs shows where microbial growth was prevented. So a larger zone means greater antimicrobial activity under equal conditions. Our next test is the use dilution test. And the use dilution test is a standardized lab method that we use to evaluate disinfectants on inanimate surfaces, non-living surfaces like surgical instruments or countertops. So this procedure involves taking metal cylinders. We're going to dip these in a bacterial culture. And then this bacterial culture is usually Staphylococcus aureus or sometimes Pseudomonas aeruginosa. These cylinders are then dried, and then we're going to place them in a disinfectant for a certain amount of time. We often use various concentrations of our disinfectant to see which concentration is effective. After exposure to the disinfectant, we take these cylinders and we incubate them in fresh media. And what we want to do is check for surviving bacteria. So in the picture below, I can see that, let's pretend this is some kind of disinfectant at different concentrations. It looks like this is the lowest concentration of the disinfectant or chemical that is effective at killing the microbes. Anything lower than 8 micrograms per mil, in this case, has cloudiness. So that means that those concentrations of the disinfectant were not effective in killing the microbe. So to pass this test, the standard results that you have to get is 59 out of 60 replicates. So you're going to replicate this experiment multiple times, many times. And 59 out of 60 replicates must show no growth. This method is thus quantitative, it's reproducible, and manufacturers use it to ensure their disinfectants meet standards set by the AOAC. That's the Association of Official Analytical Collaboration. But this is not a clinical test. It's performed under controlled conditions to verify or make sure disinfectant claims are accurate before we use them in the healthcare industry. So I just mentioned that use dilution test is not performed in a clinical setting because the use dilution test is a standard lab test that manufacturers use to evaluate disinfectant efficacy on surfaces and to validate what the product claims to do. This is really for regulatory approval, like the approval of the EPA, the Environmental Protection Agency. So clinical staff don't perform this test because they rely on these already validated products. They don't test them themselves. The next test is the in-use test. And in contrast, this in-use test is performed in clinical environments, and we use it to verify whether a working disinfectant solution is still effective or if it's been contaminated. So what we do is we take a sample of the used disinfectant and we dilute it and plate it onto growth media. If the test yields 5 or more colonies after incubation, then that means the solution is contaminated and ineffective. So this method helps hospitals monitor disinfectant integrity over time, especially when the same solution is used and reused in different cleaning protocols. So if you look at the incubation very closely, we're going to incubate 2 different plates. One of them is for 3 days at 37 degrees Celsius. The other one is at room temperature for 7 days. And a growth of 5 or more colonies on either plate indicates contamination of that disinfectant solution. What does a positive in-use test indicate? So if we have a positive in-use test, that means microbes grew from that sample of disinfectant solution. And this shows us that the disinfectant is contaminated with viable microorganisms. There are live microbes in there, so therefore the disinfectant is no longer effective for proper disinfection. So if more than 5 or more colonies grow on the test plates, the disinfectant solution should be replaced. Now let's look at emerging testing methods. This is an area of growing importance in infection control. Traditional assays like that disc diffusion test or the use dilution test were designed for bacteria, not for viruses. But we now know that certain viruses like human papillomavirus or HPV can resist many disinfectants that easily kill bacteria. So newer techniques use molecular methods to detect viral RNA on surfaces and to quantify live virus particles after exposure. Some methods will use fluorescent stains and advanced microscopy to visualize viral RNA directly. And these innovations really help ensure that disinfectants are validated against viruses as well, because viruses many of them cannot be cultured easily, and it's a big step forward for hospital infection control. All right, let's recap 13.4. For the first one, describe why the phenol coefficient is used. So the phenol coefficient was developed to compare the effectiveness of new disinfectants and antiseptics to the chemical phenol. That was the first widely used disinfectant by Joseph Lister. Remember, he was a surgeon and he applied antiseptic technique in his surgeries. And this coefficient test measures the relative potency of a chemical agent against standard test bacteria, the Staphylococcus aureus and Salmonella typhi. So a phenol coefficient greater than 1 meant the chemical is more effective than phenol. A coefficient less than 1 means it's less effective. If you get a coefficient of 1, that means it's similarly effective to phenol. Even though it's historically important, we rarely use the phenol coefficient test today because conditions and organisms back then were kind of arbitrarily chosen and not standardized for all disinfectants. For the second learning objective, comparing and contrasting these tests, I'm going to use a table and show you in the next slide. All right, so here are our tests. This is our learning objective, compare and contrast the disc diffusion, use dilution, and in-use methods for testing the effectiveness of antiseptics, disinfectants, and sterilants. So I didn't put the phenol coefficient here because it's not in this learning objective, but it also provides a historical benchmark rather than being used today. Remember, the disc diffusion method gives us a quick visual comparison. We can see those zones of inhibition. The use dilution test ensures true killing efficiency. We can see whether the broth is clear or cloudy. And the in-use test ensures continued effectiveness in real-world conditions, right? We want to make sure our disinfectant is clean. There aren't any microbes growing in there. So together, these methods allow us to evaluate disinfectants scientifically and ensure safety in healthcare and lab settings. And that takes us to the end of Chapter 13. In the next chapter, Chapter 14, we will look at antimicrobial drugs. Thanks for watching.